Welcome to our walkthrough of LeetCode problem number 784, letter case permutation. In this problem, we explore an interesting challenge involving string manipulation and permutations. This is a fantastic question to practice recursion and backtracking concepts. Let's dive right in. In this problem, we are working with a string S that may contain lowercase letters, uppercase letters, and digits. Our goal is to generate all possible strings by toggling the case of only the alphabetic characters in S. This means that each letter can either remain in its original case or switch to the opposite case, while digits stay unchanged. The output will be a list of all these permutations, and the order of the output does not matter. For example, if the input is S equals A1 B2, we need to consider every combination of uppercase and lowercase for the letters A and B. Let's break this down further with examples. Now, looking at the first example, the input string S equals A1 B2 contains two letters, A and B, and two digits, 1 and 2. Since each letter can either stay in its current case or toggle, we have two choices for each letter. This leads to a total of 2 squared, or 4, permutations. These permutations are the original string A1 B2, toggling only B to get A1 B2, toggling only A to get A1 B2, and toggling both A and B to get A1 B2. In another example, if S equals 3Z4, we only have one letter, Z, and two digits. This results in 2 to the power of 1, or 2, permutations, 3Z4 and 3Z4. In the example where S equals 1 2 3 4 5, the input contains only digits and no letters. Since there are no alphabetic characters to toggle, the only possible permutation is the input string itself, which is 12,345. This illustrates that the number of permutations depends entirely on the number of letters in the string. Digits are unaffected and do not contribute to the permutations. By toggling alphabetic characters, we explore all combinations of their uppercase and lowercase forms, while non-alphabetic characters remain fixed. The problem comes with a few constraints and edge cases to consider. The length of the string S is between 1 and 12, and it can contain a mix of lowercase letters, uppercase letters, and digits. For edge cases, if S has no letters, like in S equals 1 2 3 4 5, the output is the string itself since no toggling is possible. If all characters are letters, like S equals ABC, every letter contributes to the permutations, resulting in 2 cubed, or 8, combinations. For mixed strings, such as S equals A1 B2C, we toggle only the letters while digits stay fixed. Finally, for a single character string, if it's a letter like S equals Z, the output is both Z and Z. If it's a digit like S equals 5, the output is just 5. These scenarios ensure that the solution handles all possible inputs effectively. To tackle the problem of generating all permutations of a string by toggling the case of alphabetic characters, one straightforward idea is the brute force approach. Here, for every alphabetic character, we toggle its case to generate all possible combinations. Given that each letter can independently be uppercase or lowercase, we end up with 2 to the power of n combinations, where n represents the number of alphabetic characters in the string. The process involves recursively iterating through all subsets of the string and toggling the case of each letter. However, this method has significant drawbacks. It has a time complexity of 2 to the power of n asterisk n, because we have 2 to the power of n recursive calls, and for each, constructing the string takes n. Additionally, it uses n space for the recursion stack. The main limitation here is inefficiency for larger strings due to the exponential growth of recursive calls and redundant toggling operations, which makes it impractical in many cases. A better strategy is the optimized backtracking approach. Instead of generating all possible strings and then filtering, backtracking directly constructs valid permutations step by step. This avoids redundant computations and is more memory efficient. The process starts with a recursive function that processes one character at a time. If the character is alphabetic, we toggle its case and proceed recursively with both uppercase and lowercase options. For non-alphabetic characters, we simply add them to the current path and move forward. Once we reach the end of the string, we add the constructed permutation to the result. This method has the same time complexity as brute force, 2 to the power of n asterisk n, but avoids redundant operations, making it more practical. Space usage is limited to n for the recursion stack. The advantages of this approach are its systematic nature, reduced redundancy, and clean implementation, making it an efficient solution for the problem. Another alternative is the iterative approach using a queue, which draws from the concept of breadth-first search or BFS. Here, we treat the problem as a level-wise expansion of permutations. We begin by initializing a queue with the original string. For each character in the string, we dequeue all current strings and enqueue new strings by toggling the case of the current character. This process continues until every character has been processed. The time complexity remains 2 to the power of n asterisk n, as we generate all permutations, but the space complexity is higher due to the queue, which can store up to 2 to the power of n strings at once. The BFS-style approach has its advantages, such as avoiding recursion and being easier to debug and visualize. However, the trade-off is its higher memory usage, as intermediate permutations need to be stored simultaneously. Among the approaches discussed, the chosen strategy is optimized backtracking, and there are compelling reasons for this choice. First, backtracking is more efficient as it avoids redundant computations and directly constructs valid permutations without unnecessary intermediate steps. Second, it is more memory efficient compared to BFS, requiring only n space for the recursion stack, whereas BFS uses a queue that grows exponentially with the number of permutations. Lastly, the simplicity of the recursive structure makes it easier to handle the distinction between alphabetic and non-alphabetic characters. Some key insights include the fact that non-alphabetic characters don't impact permutations, allowing us to focus on toggling the case of letters. Additionally, the branching nature of case toggling aligns well with recursion, making backtracking the most balanced approach in terms of time and space efficiency. When comparing the trade-offs, backtracking stands out as the most balanced solution. While BFS offers ease of debugging through its iterative nature, it requires significantly more memory due to the queue's exponential growth. Brute force, on the other hand, is simple to understand but becomes computationally expensive and impractical for larger strings. Backtracking combines the efficiency of avoiding redundant computations with the memory advantage of a minimal recursion stack. In terms of complexity, the time remains 2 to the power of n asterisk n, due to the exponential number of permutations, but the space usage is reduced to n. This balance between clarity, efficiency, and memory optimization makes backtracking the ideal choice for this problem, giving us confidence in its practical applicability even for moderately large inputs. In this problem, we are tasked with generating all permutations of a given string by toggling the case of each alphabetic character. For example, if the input string contains the letter A, we must consider both that and it in the permutations. Non-alphabetic characters, such as digits or symbols, remain unchanged throughout the process. To solve this, we use a backtracking approach. Backtracking is a recursive algorithmic technique that explores all possible decisions, in this case, whether to toggle the case or not by traversing a tree-like structure. We start by initializing a list called results to store all the generated permutations. This setup ensures that we have a centralized location to collect all the valid outputs as we explore different combinations. Next, we define the recursive function, which is the core of our backtracking approach. The function, backtrack, takes two parameters, the index, which tracks the current position in the string, and current_string, which represents the string we are building at that point in the recursion. The base case for this recursion is when the index reaches the length of the input string. At this point, we have processed all characters, so we add the current_string to the results list and return. For the recursive case, we check whether the character at the current index is alphabetic or not. If it is alphabetic, we create two branches, one where we toggle the case of the character, and another where we keep it unchanged. If the character is non-alphabetic, we simply append it to current_string as is and proceed to the next index. This branching ensures that every possible combination of toggled cases is explored, and by the end of the recursion, the results list contains all valid permutations. Once the backtracking process is complete, we return the results list, which contains all permutations of the string with toggled cases. Now, let's break down some key insights about the algorithm. The recursive function operates like a binary tree, where each alphabetic character creates two branches, one for toggling the case and one for leaving it unchanged. Non-alphabetic characters, on the other hand, do not create branches, which helps reduce unnecessary recursion. In terms of time complexity, the algorithm generates two k combinations, where k is the number of alphabetic characters in the string. This makes the time complexity O2 to the power of k. For space complexity, the recursion stack depth is proportional to the length of the input string, which is O(n). Additionally, the results list requires O2 to the power of k space to store all permutations. To implement this algorithm efficiently, we rely on two main data structures. First, the results list is used to store all permutations of the string. Second, the recursive function handles the decision-making process, dynamically building permutations as it traverses the input string. It's also important to consider edge cases. For instance, if the input string contains no alphabetic characters, such as 12,345, the result will simply be a list containing the original string itself. If the input string is empty, the result is an empty list. When the string contains mixed cases, the algorithm correctly toggles both uppercase and lowercase letters. Let's walk through an example to illustrate how this works. Consider the input string A1b. We begin with an empty current_string and start exploring from the first character. At the first index, the character is A, which is alphabetic. This creates two branches, one where we add A unchanged to the current_string, and another where we toggle it to A. Next, at the second index, the character is 1, which is non-alphabetic. For both branches, we simply append 1 to the current_string without creating additional branches. At the third index, the character is B, which is alphabetic. Here, we create two more branches for each existing current_string, one where B remains unchanged, and another where it is toggled to B. Finally, at the fourth index, we reach the end of the string, so each current_string is added to the results list. The final output for the input A1b is A1b, 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 representing all possible permutations with toggled cases. This solution solves the LeetCode problem number 784 letter case permutation using a backtracking approach. The function letter case permutation generates all possible strings by toggling the case of alphabetic characters in the input string. We start by defining a helper function backtrack, which recursively explores all the possible permutations of the input string s. The function takes two parameters, index, which tracks the current position in the string, and path, which builds the current permutation as a list of characters. The base case for the recursion occurs when index equals the length of s. At this point, the current path represents a complete permutation, so we convert it to a string and add it to the result list. For each character in S, we first add it to the path as is, unchanged, and recursively call backtrack with the next index. After the recursive call, we backtrack by removing the last character from path. If the current character is a letter, we also create a toggled version of it using the swapcase method, add it to path, and recursively call backtrack again. After this call, we backtrack by removing the toggled character from path. The recursion explores all combinations, toggling the case of letters while leaving other characters unchanged. The final result is a list of all valid permutations, which is returned at the end of the function. This approach ensures that all permutations are generated efficiently, with a time complexity of O2 to the power of n, where n is the number of alphabetic characters in the input string. Here, we start by defining a method called letter case permutation that takes a string s as input and returns a list of all possible permutations of the string with different letter cases. To achieve this, we initialize an empty list called result to store our permutations and call a helper method named backtrack. The backtrack method is where the recursive logic happens. It takes four parameters: the input string s, the current index we're processing, a string builder object to build our path, and the result list to store the generated permutations. Inside the backtrack method, we first handle the base case when the index reaches the length of the string. At that point, we add the current path to the result list and return, as there's nothing more to process. Next, we look at the character at the current index. We add it to our path as is and recursively call backtrack for the next index. Once we return from that recursive call, we backtrack by removing the last character from the path to prepare for the next step. If the character at the current index is a letter, we also generate its toggled case and explore that possibility. This is handled by appending the toggled version of the character, calling backtrack again, and then backtracking by removing that character as well. The final part of the implementation contains the closing braces for the if and backtrack methods. Additionally, we define a helper method called toggleCase. This method takes a character as input and uses a simple conditional expression to toggle its case. If the character is uppercase, it converts it to lowercase, and if it's lowercase, it converts it to uppercase. This utility function is key to generating permutations with different letter cases. By combining the recursive exploration in the backtrack method with the toggling logic in toggleCase, we ensure that all possible case permutations of the input string are generated and added to the result list. This completes our implementation, providing an efficient and elegant way to solve the problem. To solve the problem of letter case permutation, we want to generate all possible permutations of the string where we toggled the case of each letter. For example, given the input s equals a1b2, we start by calling our recursive function with an initial index of 0, an empty path, and an empty result. At index 0, the current character is a, which is a letter. We add it to the path and make a recursive call with the updated index and path. Moving to index 1, the character is 1, which is not a letter, so we add 1 directly to the path and recurse again with the updated state. At index 2, the character is b, another letter. Here, we add b to the path and make a recursive call. After this, we backtrack by removing b from the path, toggling its case to b, and making another recursive call. This process ensures we explore both case options for each letter while building the path incrementally. At index 3, the current character is 2, which is not a letter. We add 2 to the path and make a recursive call. After completing this branch, we backtrack by removing 2, then add it again for the alternate path where b was used instead of b. Once the index equals the length of the string, we join the path into a string and add it to the result. At this point, the result contains a1b2, a1b2. Next, we backtrack all the way to index 0, toggle the case of a2, and repeat the entire process for this new branch. The final result after exploring all possible paths is a1b2, 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 a1b2. This approach ensures we systematically generate all case permutations by leveraging recursion and backtracking. Now let's look at another example with the input s equals 3z4. At index 0, the current character is 3, which is not a letter. We add 3 directly to the path and recurse. At index 1, we encounter z, a letter. We add z to the path and recurse further. After this, we backtrack by removing z, toggle its case to z, and recurse again. At index 2, the character is 4, another non-letter, so we add it directly to the path and recurse. Once the index equals the length of the string, we join the path into a string and add it to the result. The final result for this input is 3z4, 3z4. This example reinforces the concept that we only toggle the case of letters, while non-letters are added directly to the path without modification. Finally, let's consider the input s equals 123. Here, all the characters are digits, so there are no letters to toggle. At index 0, we add 1 to the path and recurse. At index 1, we add 2 to the path and recurse again. At index 2, we add 3 to the path and recurse once more. When the index equals the length of the string, we join the path into a string and add it to the result. Since there are no letters in the input, the result is simply 123. This example highlights that when there are no letters in the input, the result contains only the original string. The key takeaways from these examples are that we explore both cases for each letter using recursion, add non-letters directly to the path, and use backtracking to systematically explore all combinations. The time complexity of this approach is 2 to the power of L asterisk n, where L is the number of letters and n is the length of the string. The time complexity of this solution is 2 to the power of n asterisk n, where n is the length of the input string, and this is primarily due to the recursive tree structure of the algorithm. At each index in the string, the algorithm makes a decision. It can either include the current character as it is, or, if the character is a letter, it can also include its case-swapped version. This results in a branching process, where each letter generates 2 possibilities, forming a binary decision tree. In the worst-case scenario, where all characters in the string are letters, this results in 2 to the power of n nodes. For strings that include digits, the branching applies only to the letters, so the combinations are proportional to 2 to the power of m, where m is the number of letters. Additionally, for each leaf node in this tree, a string is constructed by joining the characters in the path. Since string joining for a string of length n takes n time, and there are 2 to the power of n leaf nodes, the overall string construction contributes 2 to the power of n asterisk n to the time complexity. Overall, the time complexity is dominated by the string construction at the leaf nodes, which makes it 2 to the power of n asterisk n. Now, looking at the space complexity, this solution uses space both for the recursion stack and for storing the results. The recursion stack depth is equal to the length of the input string, or n, because the algorithm uses a backtracking approach and explores one branch at a time. This contributes n space for the recursion stack. The result list, on the other hand, stores all the 2 to the power of n combinations generated by the algorithm. Since each combination is a string of length n, the space required for storing all these permutations is 2 to the power of n asterisk n. Combining these two, the overall space complexity is also dominated by the result storage, leading to 2 to the power of n asterisk n. The temporary path list, which tracks the current state during the recursion, also requires n space. However, this space is already accounted for in the recursion stack, so it doesn't add to the overall space complexity. In summary, the space complexity of the solution is dominated by the storage of the result list, which is 2 to the power of n asterisk n. This ensures that both the time and space complexities remain consistent and efficient given the nature of the problem, where we need to generate and store all permutations. When comparing this optimized backtracking approach to a brute force method, the two have the same time complexity of 2 to the power of n asterisk n. A naive brute force approach would generate all possible combinations of uppercase and lowercase letters for every character, leading to 2 to the power of n combinations, and then validate each one. The backtracking approach, however, is more efficient because it avoids redundant computations by constructing valid permutations directly during the recursive traversal. It also optimizes memory usage by maintaining only the current state and the result list. The branching factor in the recursion tree is 2 for letters and 1 for digits, so in the worst case where all characters are letters, there are 2 to the power of n leaves, each requiring n time for string construction. This confirms the total time complexity is 2 to the power of n asterisk n. For space, the result storage dominates, leading to 2 to the power of n asterisk n as well. In the best case, if the string contains only digits, no branching occurs, and the time complexity reduces to n. However, in average or worst case scenarios, where the string has a mix of letters and digits or all letters, the complexity remains 2 to the power of n asterisk n. When solving the letter case permutation problem, there are a few common mistakes to watch out for. First, it's important not to treat digits or special characters as toggleable. Only alphabetic characters have uppercase and lowercase forms, so non-alphabetic characters should remain unchanged in all permutations. A good way to handle this is by using the isalpha method in Python or an equivalent function in other languages to check if a character is alphabetic. Another mistake is attempting to modify the input string directly. Remember, strings in many languages, such as Python and Java, are immutable, meaning you can't change them in place. If you try, you'll get runtime errors. A better approach is to use a list or dynamically build new strings instead. Finally, be mindful of the exponential growth of the solution space. For n alphabetic characters, there are 2 to the power of n permutations, which can quickly become unmanageable for larger inputs. To address this, consider optimizing your approach by pruning unnecessary branches early on, especially if the problem constraints allow it. Another area to be careful with is edge cases. For example, you might encounter strings like an empty string, a string of only digits like 123, or mixed strings like a 1b. Skipping these edge cases can lead to runtime errors or incorrect outputs, so it's crucial to include them in your tests. Additionally, incorrect handling of backtracking can cause problems. If you forget to revert changes made during recursive calls, the state from one call can persist into others, leading to incorrect permutations. To avoid this, make sure to carefully reset the state when backtracking. Using helper functions to manage and restore the state is an effective way to ensure your recursive solution behaves as expected. From an interview perspective, there are some key insights to consider when solving this problem. One of the most important is distinguishing between fixed and toggleable characters. This clarity in your implementation will reduce unnecessary computation and demonstrate your understanding of the problem. Additionally, recognizing that this is a variant of a power set or subset generation problem can help you apply patterns and techniques from similar problems. The optimal approach here is backtracking, which allows you to explore all possible combinations efficiently. This is preferable to generating all permutations and filtering them afterward, as it avoids redundant work and is more computationally efficient. During an interview, it's also important to clearly communicate the trade-offs between space complexity, which comes from storing results, and time complexity, which is the cost of generating each permutation. Finally, if you're preparing for related problems, you might want to explore others like LeetCode 46 on permutations, LeetCode 22 for generating parentheses, or LeetCode 78 on subsets. There are also alternative approaches to solving the problem that you might consider. One option is an iterative approach, where you build permutations level by toggling cases. This can be easier to implement for small inputs, but it becomes harder to manage as the input size grows. Another method is breadth-first search, or BFS, where you use a queue to generate permutations iteratively. While this avoids the risk of a recursion stack overflow, it requires more memory to maintain the queue. Finally, there's bit masking, which represents toggle decisions as a binary number 0 for lowercase and 1 for uppercase. Bit masking is a compact and efficient representation, but it can be harder to debug, especially for beginners. Each of these approaches has its own trade-offs, and the best choice depends on the specific problem constraints and your comfort level with the techniques. Great job reaching the end of this problem walkthrough. To summarize, we explored how to use backtracking to solve the letter case permutation problem efficiently. This question is a fantastic example of how to leverage recursion for combinatorial challenges. Don't forget to practice similar problems to solidify your understanding. Thanks for tuning in, and I'll see you in the next one. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!